Hi everyone, and welcome to the Applied Algebraic Topology online seminar. The speaker today is Dejan Govc, and the title of his talk is Fundamental Groups of Small Simplicial Complexes.
Okay, so thanks for the introduction, and thanks for inviting me to give this talk. Let me get started. So first, we're going to take a look at this motivating example. So suppose we have the three-dimensional sphere. So there's this example of a homology sphere found by Poincaré more than 100 years ago. So the idea is that there's this action of the binary icosahedral group on the three-sphere, and by taking the quotient with respect to this action, we get a manifold which has some strange properties. And so there's this result by Björner and Lutz from 2000 that this manifold can be triangulated with 16 vertices. So if you look at this paper by Björner and Lutz, you can see a nice picture of this triangulation. So I don't have it on my slide today. And so the triangulation was found by triangulating this. So there's a representation of the space as a quotient of a dodecahedron, which has 24 vertices. And then by using this bistellar flip program that Frank Lutz came up with, they managed to reduce it to 16 vertices. So that's the smallest known triangulation of this manifold at the moment. And then in 2005, Bakci and Data, using combinatorial methods, proved that at least 12 vertices are needed to triangulate this manifold. Now, the conjecture stated by Björner and Lutz was that the minimal triangulation has 16 vertices, so this leaves quite a lot of room. In particular, we would need better upper bounds to establish such things. This is the case for most manifolds, in fact. So there's many triangulations known for manifolds, but proving that a triangulation is minimal is quite involved. So minimal triangulations have been established in just some specific cases. For example, they're known for surfaces. That's a classical result by Ringel and Jungermann. And for some other manifolds, they were established using computational methods, using some theoretical lower bounds that were known from geometric combinatorics. Okay, so how might one attack such conjectures? So let me give some context now, how I arrived at these questions. So there was this definition by Karoubi and Weibel. So suppose you have a space X, then you can ask what is the cardinality of the minimal good cover of this space. For the two spaces that you can see in the picture, the first space, so they are both homotopy equivalent to a wedge of three circles. But if you think about it a little bit, you will be able to see that for the first of these spaces, you need 5 elements in any good cover. And for the second space, you need 4. So for the second one, this is because you can just take the open stars of the vertices, so that's a good cover. For the first one, it's slightly less obvious, but the idea is that these outer sort of intervals each require their separate component, and then you need at least 2 components to make a good cover, 2 more components to make a good cover out of it. Okay, so this cardinality of a good cover is not homotopy invariant. So the idea to define a homotopy invariant is to take the minimum over all possible homotopy types of cardinalities of all good covers. Okay, there are some results classifying this invariant. So in particular, Borghini and Mignan computed the covering type of surfaces, which turns out it agrees with the number of vertices in the minimal triangulation of a surface, with one curious exception, which is the surface of genus 2. So in that case, they can find a complex which is homotopy equivalent to that surface, but has actually one vertex less. So in particular, that's not a triangulated surface. It's just a complex with the same homotopy type. Okay, now this second paper I'm mentioning here is by me and my collaborators. So we related this invariant to other known homotopy invariants, such as the Lusternik-Schnirelmann category and cohomology. And using this, we established various lower bounds, some of which were already known and some of which were new. So and in particular, we related this covering type invariant by means of the Nerv theorem to triangulations. So, in particular, CT of X is a lower bound for the number of vertices in a homotopy triangulation of a space. And then this third paper I'm mentioning here is for the case of Lie groups. Anyhow, so this is mostly just for context. I will be explaining all of the ideas used to compute, well, to relate the number of vertices in triangulations to fundamental groups in the slides that will follow. So covering type will not really be used anymore in my talk. So this is mostly just for context. Okay. Now, the main observation, which we have used in many places in this work on covering type, is this one. So if we have a triangulation of a manifold, and tau is a facet of this triangulation, well, then if the manifold is at least three-dimensional, first of all, we can remove this simplex, this facet, without changing the fundamental group, because the fundamental group of a space only depends on the two skeleton of the space. Okay, but then you can ask what happens after removing this simplex. So when we remove the simplex, somehow the rest of the space around that simplex can be contracted to the subcomplex generated by the remaining vertices, which means that if we have a manifold that has a certain fundamental group, then we can remove all of the vertices which belong to one of these top dimensional simplices. And the remaining subcomplex will have the same fundamental group. So in particular, this gives us the following corollary. So if we have a
Dejan, can I ask a question?
Mm-hmm.
If you go back one slide.
Of course.
So I understand the statement if P is like a three manifold or a higher dimensional manifold, but I mean, is this true if P is just a simplicial complex and tau might be a two-dimensional facet, or what am I missing?
So in this case, well, yeah, I think you are correct that this is not. So not everything that's stated here is true exactly in this generality. So I believe the fundamental group of P will be isomorphic to the last fundamental group, but not to the one in the middle in general, for general simplicial complexes.
I see. That makes sense. Okay.
Yeah. Okay. Makes sense. Good.
Yeah.
Okay. So the corollary is if you have a D-manifold that can be triangulated with n vertices, then there must exist a complex with n minus d minus 1 vertices, which has the same fundamental group. So in particular, Björner and Lutz took their complex and, they basically use this idea, which immediately leads to a complex that is acyclic, and has the same fundamental group as the Poincaré sphere on 11 vertices. Then by retriangulating that complex, they are able to arrive at 10 vertices for realizing that particular fundamental group. Now, if the Poincaré sphere were to have a triangulation with 13 vertices, that in particular would mean that, so upon removing this top dimensional simplex, you would need to have a complex with, let's say, with 9 vertices, sorry. Yeah, 9 vertices. So we can try to exclude such possibilities by enumerating fundamental groups of all complexes with that amount of vertices. And that's the strategy we're going to use. Now, obviously, due to this observation that I'm stating here, the best lower bound that we could get from this would be 14. Sorry, 14. Yeah, 14, because a complex on 10 vertices exists. So in principle, there could be a realization with 14 vertices of the Poincaré sphere in theory. So there's still some way to go to get to 16, which is the currently known triangulation. But the best lower bound that's currently known is 12. Well, that was known before this work, let's say, because we will slightly improve it now. Okay, so let's get started. Now, the idea then is to try to classify these fundamental groups. If you start with complexes on 5 vertices, it's quite easy to see that all possible complexes that you can get will be wedges of spheres. So look at this picture. This is a 4 simplex. Which has been embedded in, which has been subdivided by the addition of a, sorry, this is a 3 simplex, which has been subdivided by the addition of a single vertex in the middle and embedded into 3-dimensional space. This is what you arrive at if you take the boundary of a 4 simplex and remove one of its facets. So the idea here is that what you can get as subcomplexes of the 4 simplex. The first one is the full subcomplex, which is contractible, so it's kind of boring from the perspective of fundamental groups. Then if you remove the top dimensional simplex, you already have a sphere, which is simply connected, so it's also boring. And then after removing another face, this complex already embeds in 3 space and nothing very wild can happen there. So it's you get a wedge of spheres, or maybe a sum of wedge of spheres. Okay, so in particular, the fundamental group must be free on n generators for some number n, which also cannot be very high because it's bounded by the number of edges in this graph that you get. Okay. Then the next question is, what about complexes on 6 vertices? So for 6 vertices, it has been known for a long time that you can realize RP2 by taking this triangulation of the sphere by taking the icosahedron, and then quotienting by the antipodal action. And this gives you a minimal triangulation of RP2, which you can see here in the picture. So notice that in the outer circle, some vertices are identified. In particular, it winds around twice. So this is RP2. Now, by some combinatorial consideration or computationally, you can show that this is the only weird thing that can happen on 6 vertices. So in particular, the fundamental groups will be free or isomorphic to Z2. So in this case, it's still possible to enumerate all homotopy types of complexes. There's about 16,000 of them. So that's something that's quite easy to compute with the computer. But you can also do it by hand by noticing that so any triangulation of the of RP2, let me put it like this. So if you have a complex on 6 vertices, which has a non-free fundamental group, then it cannot contain two simplices that lie opposite to each other. because having two such simplices will already give you a free fundamental group by doing some Seifert van Kampen argument. So that's a way to prove by hand that if it's not free, it has at most 10 simplices. And then you can also estimate it from below by showing that, well, if you don't have 10 triangles, then the fundamental groups will again be kind of boring. Yeah, if anyone's curious, I can explain this maybe in the questions section. Okay, so anyhow, this is what holds for 6 vertices. Now we would want to have a computation for 7 vertices, but it turns out that the number of complexes grows quite fast. So in particular, there's these so-called Dedekind numbers, which enumerate how many simplicial complexes you can have on a certain number of vertices. So here I'm taking into account this convention, which is used in combinatorics, that the empty set counts as a simplex. So in particular, that means that we have 2 empty complexes. One of them is empty. That means that it only contains the empty set. And the other one is called void, which means that it doesn't even contain the empty set. And combinatorialists sometimes like to distinguish between these two complexes. And if you count like that, then you get exactly these Dedekind numbers, which you can see here. So in the first column, you have number of all possible simplicial complexes on a, let's say, n vertex set. So we are interested in this case of 7 vertices, which is the number in red, and it's quite huge. And in the second column, you can see the numbers which you get if you reduce by isomorphism. So if you only consider isomorphic complexes. There's still 490 million of them. So, and it's not exactly clear how to generate all of them up to isomorphism. So this seems quite involved to calculate. So we need some reduction.
Dejan, the second column was up to isomorphism or up to homotopy equivalence?
Up to isomorphism.
Isomorphism, I see.
Yeah.
Okay, thanks.
Yeah. So yeah, I suppose you could, I mean, it would be more natural in this case probably to ask what the number is up to homotopy equivalence, but that would probably be even harder to determine. Or maybe I might be wrong on this one. So yeah, I'm not sure anyone's done this, but if you know of such a paper, let me know. I mean, I'll be curious because then it simplifies the arguments quite a lot. Okay, so the first observation to reduce this number further is that without loss of generality, we can assume that the complex is pure 2-dimensional. This is because the fundamental group is determined by the 2 skeleton, so we can forget the rest of the complex. And then if you have a maximal edge, that maximal edge will only, so if it's between 2 separate components of the, well, of whatever is formed by the triangles, then it will connect the 2 components, which corresponds to a wedge sum. And if it's in the same component, then it can contribute only an S1 sum end to the wedge. So that means to determine the 3 factors of the fundamental group, we only need to know what happens for the pure 2-dimensional complexes. Now, these complexes, so pure 2-dimensional complexes are exactly the same thing as so-called 3 hypergraphs in combinatorics. So in combinatorics, people, or graph theory, people sometimes, well, people classically study graphs in graph theory, which are, so you take vertices and then you have edges which correspond to 2-element subsets. Now, if you generalize this idea and just take arbitrary subsets, so you can think of those subsets as hyper edges. And graphs where the hyper edges are 3-element subsets would be 3 hypergraphs. Now, 3 hypergraphs are basically the same as pure two-dimensional simplicial complexes. But thinking of them this way allows you to count them, because there's this Polya-Redfield theory, which allows you to count orbits of certain group actions, and then you can use this idea to count them, and you can generate all of these numbers here. So all of these numbers can be determined explicitly by a simple procedure. I should probably say that this is not the case for Dedekind numbers. So notice the question marks here on the previous slide on the bottom. It's actually an open problem. What is the 9th Dedekind number? Now that's kind of funny, because there was a closed formula found for the Dedekind numbers, but this closed formula is so messy that it's impossible to compute actual numbers from it. So case of 9 vertices is wide open. Okay. Anyhow, so taking just the pure two-dimensional complexes reduces their number to 7 million, and that's something that might already be computable by hand. So let's try to do it. Okay, so to do the computation, I'm going to use this lemma that I have in another paper. So the most basic way of establishing that a complex is a wedge of spheres is by taking some top-dimensional simplices and then showing that upon removing those simplices, you are left with a contractible subcomplex. Now, then by contracting that subcomplex, you have a wedge of spheres. So the original space must have been a wedge of spheres. Now, generalizing this idea slightly, you can show this result. If you have a subcomplex of your complex, which has this property, so if you look at the space completely on the left, so there's this space that's drawn in black. Now that subcomplex has this property, right? If you remove the red and blue simplices, then it will be contractible. But then you can perform this contraction in the larger space, and in particular, this shows that if you find such top-dimensional simplices that upon removing them from this bigger space, you will get a contractible subcomplex. Then these two simplices just contribute some spherical wedge summons to the homotopy type. That's the idea. So then you can pop these top simplices, and you know that what you get after popping these two simplices, which is the space you can see in the middle, will be homotopy equivalent to the non-spherical wedge summon, let's say. Okay, and you can do this computationally. And this allows you to simplify homotopy types in this way. So I call this procedure cone and collapse, because I don't really pop the simplices. Instead, I do the cone over the whole subcomplex, which has the same effect, but behaves in a better way, computationally speaking. Now, this is purely heuristic. I don't know why it behaves better, but practice shows that somehow it does. Okay, so now the procedure to do the computation is you can generate all of these two pure complexes using this software by Brendan McKay called Naughty Gang, which means graph generator. So this generates all these hypergraphs that we need, and then you can test the complexes to exclude obvious wedges of spheres. I use Mathematica to do this, so it's not computationally too involved. I didn't have to learn some crazy C++ or something to do it. And you're left with only 600 complexes, which do not have obvious homotopy types. Now, for these remaining 602 complexes, you can compute their pi1 in SageMath, and this gives you the answer. So that's the result. So on 7 vertices, we can only get 3 groups. we can get free products of Z2 and some free group. And we can get Z times Z. Now notice that Z times Z is the fundamental group of the torus. And it has been known for a while that the minimal triangulation of the torus, in fact, has 7 vertices. So that's what we see here. The important thing for me here is that, so as a consequence of this result, we can immediately see that we need at least 12 vertices to triangulate the Poincare sphere, because binary icosahedral group is not one of these groups we see in the list. So this reproves the result by Bakchi and Data. Although, to be fair, Bakchi and Data did it in more generality because they considered homology spheres of any dimension. So, but this does the job for Poincare sphere in particular. Okay, now
and their proof was probably sort of non-computational, right? But now you're going to use this computational approach and prove on their result.
Yes, yeah, definitely. So their proof was by examining a large number of cases, and it's purely combinatorial. So yeah, it's I'd say quite a lot of effort goes into that proof. But I mean, it's yeah, the result has been the best one for the Poincare sphere up to now, let's say. And it's I also have to say that to some extent their result is sharp because it works for Z2 homology spheres, and length spaces are an example of that. And it's known that you can get length space L31 on 12 vertices. So in that case, their result is sharp. Now for the Poincare sphere, we need something different. I mean, so the Poincare sphere in particular has a more complicated fundamental group than length space. Okay, so on 8 vertices, okay, if I repeat what I said before, we have this huge number of non-isomorphic complexes, but already reducing to 2 pure complexes, we still have more than 1 billion of them, almost 2 billion non-isomorphic complexes. So generating them all on my laptop was kind of too slow for my taste, so I didn't really want to do that. Might be doable using a supercomputer, but I wanted to have something quick. So so I'm going to do some further reductions and show you how to do this on a laptop. Okay, so there's some observations that we can do. So any complex on 8 vertices can be represented in this way that you see in the picture. So you can take 7 vertices, and the 8th vertex will correspond to will be like an apex of a cone over a subcomplex of the complex that you got on the 7 vertices. So this is the decomposition that you can see in the picture. So the complex that's drawn in black here, which I call Y, is the complex on 7 vertices. And then by adding the 8th vertex, you're effectively doing a coning operation over this complex on 7 vertices. So, and this representation makes it sort of easier to control what's happening. Okay, now furthermore, we can assume that this complex X on 8 vertices has no free faces. This is because you can just collapse the free faces, and this preserves the homotopy type and hence the fundamental group. You can also assume that Y, so this is the space on 7 vertices, is connected and pure 2-dimensional. Now, why pure 2-dimensional? Let's see. So this is because, yeah, if you have any maximal edges, if you have any maximal edges, so you will have to so yeah, if you don't do a cone over such a maximal edge, then it only contributes some sphere S1 wedge summand, and if you do a cone over it, it contributes a triangle. Now you know that this edge cannot be free. Since it cannot be free, it has to have at least 2 triangles. And you will not be able to get 2 triangles by doing just a single coning operation. So that's why you can assume there are no such edges. You can also assume it's connected, because by doing this coning operation, you would just be getting some wedge again. So that's also not something that can yield new fundamental groups. I mean, other than free products of what you already know. Okay. Now, next, we can see that if A has some number of components, then we can think of doing this cone operation over these components as doing each cone separately, and then doing another cone over the apexes, or how do you say yeah, I don't know, over the apexes of these cones. Which just corresponds to adding some S1 summands again. So what you do here is you're basically just doing a series of coning operations over this space Y, and then maybe you're adding some number of S1 summands. Okay, and what you can notice by Seifert-van Kampen is that each time you do this coning operation over some component, you're effectively just doing a quotient of the fundamental group. Now, what this means is that if the fundamental group of Y is not complicated enough, then also the fundamental group of X cannot possibly be very complicated. So here we make another reduction, which is almost without loss of generality. So we're going to lose some information here, namely in the end result, I won't be able to state exactly which cyclic groups can appear, because this information is lost. I discard it here. So so for the rest of this computation, I will assume that the fundamental group of Y is not one of these groups that you can see listed here. So it's not trivial, it's not Z, and it's not Z2, because quotients of these groups cannot be very interesting. You can only get something cyclic, or yeah, basically just cyclic groups, and we already know those to some extent, let's say. I will comment on this later again. Okay, so this loses some information, but the upside is that we have only 300,000 complexes out of those 7 million complexes that we considered before, so on 7 vertices. And now we're going to do cones over these 300,000 complexes that remain. But before we do this coning thing, then let's make some further assumptions to simplify a bit more. So you can assume that this complex A, that is the subcomplex of Y that you're doing the cone over, is at most one-dimensional. Now that's because if you have a two-dimensional simplex and you do a cone over that, you will get a three-simplex. And you already know that that doesn't affect the fundamental group. So you can simply discard such simplices, and this will not change anything. We can also assume that this complex A contains all the free edges of Y. Now this is again because of this wedge something that I was mentioning before. So we are not interested in circular wedge summands. Now this reduces the number of complexes that you can get significantly, because now you can, so now the strategy is that you just generate all of these cones in this way. So you generate these 300,000 1000 possible complexes Y, and then you do all possible cones over these subgraphs of them that you have. And so this leads you to roughly before we had 2 trillion complexes, now we have 4.5 billion of them. So that's a big reduction. And this is now possible to treat with a laptop, right? So that's kind of cool. Okay, now another observation that I will use to simplify the situation a bit further still is that because I still don't want to analyze all of these complexes in detail, so you can do this reduction here. So if you can find the decomposition of this complex on 8 vertices such that on one side you have so in 4 plus 4 vertices, such that on one side you have 3 triangles and on the other side you have 2 triangles, then you again know that the fundamental group cannot be too complicated. So this is also by some sort of a Seifert-van Kampen argument, but it has to be generalized a bit because this complex in the middle is not necessarily connected in this case. So this additionally gives you here a potential free sum and Fn here. So basically from such a complex you would get some quotient of Z, which is a cyclic group, and then maybe we have a free product with some free group. So that's what we get from this step. Okay, so we know that this case does not have to be analyzed separately. Okay, now this brings us to our main procedure. So we generate all of these conical decompositions, and then you test for this 4 plus 4 splitting condition. And it turns out that most of the complexes do have at least 3 simplices on one side and at least 2 on the other side, which means they can be discarded immediately. And this leaves you with about 4 million complexes. Now, you could do the computation for all of this directly, but I preferred to reduce it a bit further by using cone and collapse and this without loss of generality that I assumed here. So I will not go into specifics here because it's not so important, but the main point is that after this you are left with 200,000 complexes, and you can compute the fundamental group of these complexes directly using SageMath. And this brings us to the result. So for any complex on 8 vertices, the fundamental group is the free product of G and some free group, where G can be one of the following. So it can either be the cyclic group, it can be the group of the torus, it can be the group of the Klein bottle, or it can be the braid group on 3 strands, which is also isomorphic to the trefoil knot group. Now, these first 3 groups were known before because it has been known for a while that the Klein bottle has minimal triangulation with 8 vertices. So in particular, that was known. But it appears that the braid group is a new one, at least according to what I learned from conversations with Frank Lutz. So Frank Lutz told me that so I know that the cyclic group can be realized on 2, the cyclic group Z2 and Z3 can be realized. So Frank Lutz told me that also Z4 can be realized on 8 vertices using this idea of what are they called? Adamart matrix torsion complexes. There's a nice paper on this topic. But yeah, this braid group appears to be new.
Quick question there, Dejan. So this is you're taking the free product of G in this group Fn. I mean, yes. G could also be the trivial group, right?
Could be, yeah.
Yeah. Okay, I'm with you.
Okay, cool. Yeah, then Frank encouraged me to produce a picture of this complex that we get from the break group, and this is the picture that we get. So this is the new triangulation that that the computation discovered. So as you can see, this is an annulus, which is triangulated in a certain way, and some of the points, some of the vertices in the outer circle and in the inner circle are the same. And in particular, you can see that in the inner circle, you go around twice, and in the outer circle, you go around 3 times, which exactly corresponds to this relation that you have in the trefoil knot group, that a to the 2 is equal to b to the 3. And well, which is also, well, yeah. So upon presenting this example at a recent workshop I've been at, Łukasz Michalak discovered that by adding some extra triangles to this example, you can realize the symmetric group S3 on 9 vertices. And he also found some triangulations corresponding to the bounce-like solitar groups, so which I thought was kind of interesting. So I'm mentioning it here. But for the main result, corollary of this computation is that any triangulation of the Poincare sphere has at least 13 vertices. Now, there's some hope that this method could be extended to 14 vertices by doing a complete classification of fundamental groups for 9 vertices, but that is, let's say, work in progress. So yeah, that's it from me.
Okay, thank you. Maybe I would ask everyone to unmute themselves now and clap.
Thank you.
And now it's time for questions.
I was wondering if you could describe any more of this work in progress for 9 vertices. So are you thinking of about more sort of mathematical reductions, or thinking about involving folks with supercomputers, or some of both?
Yeah, I think in that case, probably both of those will be necessary. So because for 9 complexes, if we see this number here, so as you can see, the number of pure 2-dimensional complexes on 9 vertices is kind of huge. So what's that? 53 times 10 to the 18. So yeah, no hope for classifying all of them, but yeah, I've been thinking about some reductions. So far I was not successful in reducing them enough to be able to do it, but I'm seeing some rays of hope, let's say. So I think it might be possible to reduce it maybe to the order of 1 trillion or something by if some of my ideas work out the way I hope them to, but that's not been proven conclusively yet. So it's yeah, if we're optimistic, maybe it will work with the supercomputer. Now, okay, there's also the possibility that we might find an actual triangulation of the binary icosahedral group on 9 vertices. So if that happens, then it shows that at least for the case of the Poincare sphere, it doesn't work that way. So then new methods will be required.
Are there particular groups that, so you mentioned this work by the person who saw your talk and then realized fundamental groups of symmetric group on 3 symbols and this solitary group with 9 vertices. Are there do people have fundamental groups in mind? Sort of like, I conjecture this fundamental group is simple enough, maybe you could realize it on 9 vertices, or not really? There's not really conjectures out there like that.
So I know that in this work by Lutz and his collaborators, there have been, so on Adamard matrix torsion that I mentioned before, there have been some construction of complexes that have other kinds of torsion. So I think they realized Z5 and up to Z9 or something on 9 vertices. I don't remember exactly. But yeah, so there is some work being done. In particular, this question of what kind of torsion we can see on small simplicial complexes is quite an interesting open question. So it's been known that there are these torsion burst phenomena where if you sort of generate complexes on some quite small number of vertices randomly, triangle by triangle, then at some point the torsion will explode. And those explosions can be sort of huge. So I think there's some complexes on 13 vertices that have a torsion of the order of 10 to the 30 or something like that. And yeah, it's kind of fascinating.
Any further questions? Okay, so in that case, I'm gonna stop the recording and feel free to ask the questions afterwards. Dejan, thank you so much for the talk.
Yeah, thank you.